Good morning. Welcome to this presentation of introduction of the progen between my two universities, the University of Sheffield under the supervision of Professor Joseph P. Ariti and Stockholm University under the supervision of Professor Belen Martin Matute. The main title of this project is a synthesis of N-Heteroaromatic and Imine compound and can be separated in two different categories. The first project was done at the University of Sheffield and concerned the stereoselective synthesis of atropisomers via boron-directed cycloaddition and the resolution of this compound. The main was the synthesis of highly functionalized pyridine boronic ester as heteroaromatic compounds. The second part was done at Sheffield University and concerned the synthesis of imines via photooxidative coupling of amine, and for the synthesis of imine and base-imidazole, and all directed by MOF catalysis. As you can see in the title of this first project, they have a lot of funny words and it's important to pay attention to some of them. So at first I will show you and explain what an atropisomer is. Atropisomers are stereoisomers resulting from restricted rotation about second bond when the energy barrier is high enough to isolate the different isomeric species. Based on this, we can classify three different groups. The first one didn't consider proper atropisomer because the axial rotation is too fast to permit the isolation of the both species. The third class is the compound of interest, the proper atropisomer, as the energy barrier prevents the entire conversion, and they are kinetically inert. As everything is not black and white, we have here a gray area, is the class 2, where they can be considered as atropisomer, but the stereochemical integrity can be compromised over the time. As previously explained, atropisomers result from the indirect rotation about the single bond, and they can be found in common compounds as natural product, pharmaceutical, or agrochemical. Here, for example, one of the most famous is the streptonegrin, an anti-cancer and antibiotic. So for T compound, they are very challenging. A true challenge to prepare with the control of stereochemistry. So the big question is, can we devise an efficient and versatile route to this compound? Well, yes, it's possible. If, for example, you're using a diene bearing a Lewis basic donor group with a dienophile, here an alkyne bearing a Lewis acid, the coordination between the base and acid can promote the cycloaddition rate and control the regiochemistry. As here, for example, we have the triazine reacting with an alkyne bearing bipine, and after 2 days of reaction at 180 degrees in a seal tube, we can obtain the compound of cycloaddition but in 11% yield. And for example, if you're using the same alkyne bearing a salt, the BF3K, we can form EC2 a Lewis acid, we can react with the triazine and providing the product of cycloaddition in 84% at 40 degrees and just after 10 minutes. Here is a scheme of the different steps that can be included in this project. And we can see that in all of them, the boron plays a major role. For the cycloaddition, as from in the chiral compound, for the resolution, as an handle to introduce chiral tether and obtain 2 different diestereisomers, or even the boron can after provide a handle to further elaborate different product. In a more practical way, we start now for the synthesis of the first coupling partner to form the atropisomer. So we start with 3 different cyanoquinoline derivative compounds, and by reaction with the hydrazine, we form the compound B intermediate, the amidrazone, and by reaction of the diketone, the condensation provides the triazine. So this reaction was tried with 3 different compounds and provide the good to excellent yield in all these cases. The R group was directed by the diketone provided in this case methyl or phenyl group. The second coupling partner was obtained by starting with the iodobenzene bearing in ortho position a methoxy group or an ethyl group. We'll come later about this. So in this scheme, we start with a Sonoga-Chiral coupling, followed by deprotection to obtain the free alkyne. By reaction of N-Billy for the deprotonation, insertion of 3-methoxyboronate, and after reaction with the salt, the KHF2, we can obtain the product as a precursor for the Lewis acid. So now, as we have the both coupling partner synthesized, we can start now the first trial for the cycloaddition. The scope of the cycloaddition was tried first with the quinoline, and in all the cases we can see that we obtain the product of cycloaddition in a good yield, so 67 to 86%. And in this part, it's important to notice that the BF3K salt, the physical state of this compound, have a major impact on the yield of this reaction. After crystallization, we was able to increase the yield by more than 30%. This reaction was continued with the isoquinoline derivative and provide the same range of yield in the both compound bearing methoxy group or ethyl group and methyl and phenyl group on the pyridine cycle. The reaction was finally continued with the pyridine bearing methyl group on the pyridine cycle and the methoxy group, and we obtain also a good range of yield. So now that we have done the first trial with the cycloaddition, we can start the next step, the resolution of the chiral compound. To obtain the two different atropisomer and diastereosomer, we start in the reaction with the product of cycloaddition, BF2, by forming the burning acid under NaOH in THF, and after adding the chiral tether, here the R-binyl, we obtain two different diastereosomer. In the previous study, we can see that we obtain a ratio of 1:1 of the both diastereosomer. Same for the compound just at the right. With the ethyl group, we obtain also a ratio of 1:1. It was interesting to notice that in the case of the methoxy group, we obtain a ratio of 4:1 in both cases of the quinoline and the pyridine. It could be explained as the oxygen could interact with the boron to obtain a flat intermediate present here at the middle, and this possibility can lead to two different compounds, two different atropisomers, and the one with the lowest energy will be the major one. Following the previous result, we try to see if we can have an impact on the ratio. So we try here with the ratio of 4:1 on the quinoline buried methoxy group, adding another equivalent of binyl, and after 1 hour to 72 hours, we observe the same ratio of 4:1. In parallel, we try also with the ethyl group, and as we can expect it, we don't have a heteroatom to interact it, so we thought that it will not change. It was confirmed after adding one equivalent of binyl to 1 to 3 days, the ratio was still 1:1. So at this point, we don't know if we have a kinetic or a thermodynamic ratio. Something interesting happened with the compound presented on the left, the quinoline with the methyl group and the methoxy. With the ratio of 4:1, we was able to isolate an excess of 24:1 by crystallization in cold toluene. And this new ratio, after heating at reflux in toluene for 1 hour, we returned to a ratio of 4:1. We try in parallel with one bearing not methoxy group but ethyl group to have a ratio of 1:1 to obtain only one of the both diastereosomer. By separation by HPLC, it was possible, and this ratio of only one diastereosomer, we try to reflux in toluene for 1 hour, but we didn't return to a ratio of 1:1. We only observe one diastereosomer. Could include that we could have probably a thermodynamic ratio. After the previous result, we continue by working on the scope of this reaction. So first on the quinoline one bearing methyl or phenyl group, we observe the same range of yield, around 50% to 57% in the case of the methyl bearing the methoxy one. In the case of the isoquinoline, we observe a better yield for the different compound, and the same ratio was observed at 4:1 for the both bearing a methoxy group, and a ratio of 1:1 in the both-bearing and ethyl group. In the last part, we try to have another impact on the ratio by changing this time the chiral tether. For in the first case, using the dibromobinol, or in the bottom the vanol, as a more indirect molecule could maybe have a positive impact on the ratio. But unfortunately, in both cases, we obtained the same ratio at 3:1. We didn't change over time to 1 to 2 days of reaction. So in conclusion, we proved that the reaction of cycloaddition is an efficient way to provide highly functionalized pyridine-boronic ester, obtaining two different diastereomers, and the resolution was possible by insertion of aryl, showing potential dynamic thermodynamic resolution in this case. In the near future, we can work next on functionalize it by adding a different functional group by replacing the boron to confirm the stereospecificity. Now we start to pass on the next project I've done at Stockholm University for the synthesis of imine via MOF photooxidative coupling of amine. There are different ways to synthesize imine. We all know the classical approach for the condensation of carbonyl with amine. We have also catalytic method for the CN oxidation or for the dehydrogenative coupling of amine. And for this part, we can have via transition metal catalysis, as showing here a condensation of two amine by iron catalysis. We can obtain an hetero or a cross condensation. And we can have also MOF catalysis. And here we show a reaction recently reported by Chang and co-worker, showing it was possible to have the self-condensation of a benzylamine substitute under air and light directed via the MOF PCN222. For the people who is not familiar with the MOF or metal organic framework, they are porous material involving strong metal organic linker interaction. Here in the first scheme we have a straightforward synthesis of the PCN222 by Martin Matute group, where the metal at the center can be introduced to have a PCN222 metallated or not. Here we have the zirconium playing the role of the metal and the porphyrin in red playing the role of organic linker. And this pattern can be extended in a 3D structure, showing just below we can have a tunnel with a large channel and pore. We can facilitate the interaction of the substrate and the metal, and by this way increases the catalytic efficiency. So the aim of this project will be use the MOF PCN222 as catalyst for the photocatalytic oxidative coupling of amine. But in our case, we try to develop a protocol that give high selectivity for the product of cross condensation and not self-condensation. In this project, we chose as model of reaction the benzylamine and the aniline, providing a true product of cross condensation A or self-condensation B. In the initial condition, we use the PCN222 unmetallated at room temperature after 1 day with a light bulb, white light, directing on the reaction. We have a ratio of AB of 1:6 and only 12% of conversion. The first optimization, A, we change for a metallated PCM, the palladium 1, at the same condition room temperature and 1 day. We obtain a ratio of 1:3, so we decrease the ratio of the self-condensation and obtain a conversion of 15%. In the second optimization, optimization B, we increase the temperature at 60 degrees, and after 1 day we obtain a better conversion of 30%. The third optimization, the C, we increase the time at 4 days and using slow addition on the benzylamine on a mixture containing the aniline and the MOF. And we obtain a ratio this time 15:1. So in the first part we obtain a higher ratio in favor of the cross condensation with a conversion of 98%. And the last optimization, the D, we're using this time a white light strip with a higher intensity, and this time we provide a full conversion and observe only formation of the product of cross-condensation. For the scope of this reaction, we try first by adding substituent in the para position on the benzylamine and see the impact on the reaction. In all the cases, we obtain full conversion of the starting material with moderate yield to good yield for the compound A, and with only the product bearing a fluoro in the para position, we obtain a ratio of 10:1. In parallel, we work by adding substituent on the aniline for this reaction, and even if the yield was moderate to good yield depending on the substituent, we obtain in all the cases full conversion of the starting material. With the methoxy or the 3-fluoromethyl group and the chloro, we obtain a ratio of 10:1 to 1.51:1. But in the case of the compound at the top right, the orthophenyldiamine, we obtain the benzimidazole and we observe only the benzimidazole. And with this result in head, we try to work on this reaction. So in this last part, for the reaction to form benzimidazole, we try to adding different substitution on the benzylamine or the orthophenyldiamine. And in the case, we obtain also full conversion and observe different ratio of yield to moderate bearing methyl group on the orthophenyldiamine or chloro group, to good yield when the substitution was on the benzylamine, as for example the methoxy group or the bromo. Based on the reported literature, we can propose here a mechanism for the photooxidative coupling MOF directed. By light irradiation of the MOF, we can observe a ligand to cluster charge transfer from the porphyrin to the zirconium. We have generation of hole and electron who possess different property, oxidative and reductive. And with this, we can reduce the oxygen by a radical anion oxygen, and the benzylamine we can oxidize through a radical cation. By proton transfer, we obtain two different radicals, and by releasing the peroxide, we can obtain the first imine. This imine can react with another benzylamine to obtain the first product of self-condensation, and by reaction with an aniline, we can release the benzylamine and obtain the product of cross-condensation. In conclusion, we show that the oxidative cross-condensation of benzylamine with aniline via MOF catalysis was possible, to leading only on the product of cross-condensation or a major impact on the product of condensation. The best result was obtained by slow addition of the benzylamine, and the light irradiation play a major impact on the conversion. In the future, we can work on improving the yield of some substrate by changing the light source to a more powerful one, and investigate the recyclability of the MOF for this catalyst. It is now the end of this presentation. I would like to thank my board supervisor, Professor Joseph Ariti, and Professor Belin Martin Mathieuti, to help me and guide me in this project. I would like to thank my board's research group and the European to funding this project. Thank you for your attention.